Welcome to Analog Microelectronic Circuits lecture. This is lecture number 2, unit 2. And from previous class, we started discussion on bipolar junction transistor. So the three-terminal device, what we have discussed in the previous unit was MOSFET, and in the previous class, we started bipolar junction transistor, where we looked at history and understood how BJT revolutionized the semiconductor industry, and we mentioned about one difference between MOSFET and BJT was one is identified as a unipolar device and other one is identified as a bipolar device because the current conduction is due to both the charge carriers. And then we also looked at the topics what we will see in this unit, and then we have come to the device structure. We understood there are three regions, two PN junctions which can be biased in four ways, and that lead to four different modes of operation and respective applications, right? And then we have looked at two DC numericals just to see your understanding on how you can solve numericals based on DC. So in today's class, we will go ahead and we'll see the operation of an NPN transistor. We'll also try to understand how to write current equations of the transistor so that we can look at the different configurations, and later we can go for the small signal models, and finally we can come to the amplifiers, because the whole idea of this course, analog microelectronic circuits, is to introduce amplifiers to you guys, because amplifiers is one of the important circuit block which is uh, in widely used in these days, from widely used all the times to amplify weak signals, because we always deal with signals which are weak in nature, and to strengthen such signals we need circuits which can give a larger magnitude, that is your amplifier. And MOSFET and BJT are key elements which plays a very crucial role in such circuits. So with that intro, we will go to bipolar junction transistor, the operation of bipolar junction transistor. Uh, so we have looked at the structure, and we understood that there are four different modes of operation, like active, saturation, cutoff, and inverse active. And in active region, we know, or probably you have heard in your basic electronics course, that amplifiers or BJT amplifiers basically work on the region of active region of operation, right? The same reason holds good. The same understanding of MOSFET holds good here, because in active region we can actually get mm, some we can get the behavior of MOSFET close to a current source, where I can get some kind of amplification, right? So with that intro, I'm just starting. We'll straight away go and see the operation of BJT in active mode. Let me take NPN transistor as an example. So operation of NPN transistor in active mode, right? So since we are familiar with the structure, I'll just draw the structure, which is having three regions. Uh, in textbooks, often you see all the three regions are marked almost equally. At least collector and emitter will have equal sizes, but actually it is not. For understanding purpose, initially they'll keep, and later. So our understanding should be in such a way that even in doping as well as in the area wise also, there is some difference. So these are NPN regions, and from each region, you will have one terminal. So this is from N region, this is from P region, and this is from the other N region, right? So to identify the three terminals, we call this as emitter. This is base terminal, and this is collector terminal, right? So yeah, we will look at the symbol again. So if I say, look at the symbol of NPN transistor, it is like this. So this is emitter, this is base, and this is collector, and this is N, this is P, and this is N, right? Now, since I stated that we'll be looking at the operation of this NPN transistor in active mode, I'll be biasing two junctions, two PN junctions in such a way that the junctions will be in the emitter based junction will be in forward emitter based junction should be forward biased, and collector based junction should be reverse biased. This is an understanding when we say active mode. Now, now to make emitter based junction forward biased, I will be connecting. Since emitter is N, I'll be connecting in this form a battery, and I'll write this name. I'll just name this voltage as VBE because base is positive with respect to emitter, so that that PN junction will be forward biased. Similarly, to make the collector based junction reverse biased, I have to connect negative to base and positive to collector, and I'll call this as VCB because collector is positive with respect to emitter. So this is plus minus, this is plus minus. Now you can see that the effect will be on these two junctions. So this junction will be forward biased and this junction will be reverse biased, right? Now just to understand about the just to know about the three different regions, emitter is typically doped heavily. So the meaning is there will be more free carriers since it is heavily doped. Base will be very lightly doped, and your collector region will be moderately doped. This is how the doping in each region. So I hope you understand what is a doping. Doping is actually introducing impurities into a semiconductor because if the semiconductor is in its purest form, we call it as intrinsic semiconductor. By adding impurities, we can make it more conductive. That is by turning your intrinsic semiconductor into extrinsic semiconductor. Now, under this condition, so let me look at both the junctions. Now you have the emitter based junction forward biased. So if that is the case, now we know that the majority carriers in this emitter region is electron. Since the majority carriers are electron and this junction is forward biased, what will happen? Electrons will be injected into this region, right? Electrons will be moving into this region, and you have base region where you have holes, and holes will be actually moving into this region. So this happens even though this is under the under forward bias. Since it is forward bias, even the process by which the current conduction is possible here, we call it as diffusion process. Why we call it as diffusion is because uh, if you look at these two junctions, since it is forward biased, electrons are actually trying to move from a region of its higher concentration to a region where it is having lower concentration, and similarly for the holes also. But we know electrons, when it reach this base region, base is basically a p-type region where the majority carriers are holes. Now when electrons reach the base, electrons are actually minority carriers in the base, right? So one thing to note here is since electrons are flowing moving from emitter to base, electrons are moving in this direction. So the current direction is identified opposite. I hope I discussed this even in the beginning in one of our introduction lectures. Electrons are discovered after electrons are discovered later. Even before the initial assumption was the current conduction is due to the movement of positive charges. So for that reason, always whenever we mark current flow in this direction, actually the electron flow happens in the opposite. So we maintain this for the convention, because initially it was followed that the current is due to the movement of positive charges. That is why often you will see that the actual current direction even though the the flow of charges, flow of electrons makes the current, we always mark the current direction as opposite. I hope you would have observed that many times. Now, since electrons are moving from emitter to base, the current flow we mark in the opposite direction. So emitter current is actually flowing like this. Say I'll mark it as IE. Later I'll talk about the equation for all these things, right? Now similarly, now we can see mm, holes, right? Holes are actually moving from base to emitter, that constitute the whole the current in the base, which is basically due to the majority carriers in the base region. So I mark current direction in base in this form. I mark it as IB, right? So that is about the junction, emitter base junction. Both the charge carriers will move, and that will actually constitute emitter current and base current. And one more thing is, base is very likely dot, but more number of electrons are coming to the base. Some will be recombined with the holes there, right? But the rest or the many will be actually available in the base, but those electrons will be attracted by the electric field which is set up in this depletion region. Or you can see that there is a high positive positive voltage connected towards the collector, so that will actually attract the electrons, and electrons will actually, all the electrons will be collected by the collector, right? So electrons are collected by the collector, and it will take this shape this way to move, right? So the actual current direction will be, 1 second, yeah. So the current, since the electrons are moving in this direction, we will represent the current direction here as this. This is IC. All right. So this is what happens. So from base to collector, there will be a movement of charges, and that will be further here. All right. So let me note on few points here. Emitter base junction, you have an emitter base junction. So that is forward biased, due to which you have injected electrons from the emitter that will reach base. But there, those electrons are actually minority carriers in the base region. I'll take questions. Let me just finish this. Now, few electrons will be recombined. Few electrons will be recombined. The reason is, yeah, so a lot of electrons are coming into the base, but the base region itself is very small. Few will be recombined, but majority will be collected by the collector because of the large positive voltage which is available on the right side, right? Okay. Now, just all right. So so this is what is happening in an NPN transistor, and with respect to the current in an NPN device, NPN transistor. Now, if you have questions, please put in the chat box. I can discuss that, and then we will move to the current, uh, components of this. Are there any questions? All right. So let me check with specific people. Chaya, are you there? Chaya BS? Nisha Gadigeri? Huma?
Yes, sir.
Do you have any questions, Huma, now?
No, sir. Not right now.
All right. Irshad? Irshad, are you there? Jayaditya?
No question, sir.
Okay. Jivita?
No questions, sir.
Okay, okay, all right. So let me proceed. Yeah. Now the important thing here is, now when we write the current equation for an NPN transistor or for a transistor, we know that the transistor is having PN junction. So we should know, we should be familiar with the current equation of a PN junction diode. So for that, I'll just start with the current equation of a diode so that the same thing can be extended to BJT. Right. Now, so if you look at a PN junction diode, right? Say this PN junction diode is forward biased. Yes, Akram is having one question. So IB is due to minority electrons or majority carrier electrons. Okay. So IB is basically due to the movement of holes from base to emitter. Movement of holes from base to emitter. Is it clear, Akram? But we do have many components. So if you specifically look at the different components, we have to actually capture many items there that we generally not do now, because for us we will take IB as a total component IB. That I'll tell you how we will take up for in the circuits. But in device physics, we have to look at the various contribution, like how much factor is from minority, of what is majority. All those things we'll do separately in device physics when we do. So as far as circuits is concerned, I'll take up directly the IB current as a whole lump sum amount. Like it's not like we'll not see the split up what are the constituents. So majority, but mainly I can say the whole movement from base to emitter is constituting a base current. All right. Okay. Yeah. Now, for a PN junction, say there is a voltage applied between the terminals. Say it is V forward VF. Right. So then, if it is for a forward bias PN junction, I can write the diode current ID as. I hope you can recall this expression what you have done in your basic electronics, e to the power of VD. Sorry, not VD. Now it is VF divided by eta Vt minus 1. Can I get response from you guys whether you are familiar of this expression? Where we call this Is as reverse saturation current. Reverse saturation current. Vt we call it as volt equivalent of temperature. Volt equivalent of temperature. And eta is a factor. In most of the cases, if we consider it as one some values, so you can consider that eta factor as 1. So then ID is your diode. This is how you represent diode current. Yeah, I saw some response from you guys. Yes, I think you are familiar. So the same expression we will consider even here. Now. So now I'll straightforward, I'll write the current in the collector, because the whatever electrons are flowing from the forward bias PN junction is reaching collector, and that collector current can be written as the current coming, the flow of electrons from the emitter can be written as Is into e to the power of okay. Now one more thing, this is often approximated as, so if you look at this, you have two components here, Is into e to the power of Vt minus Vt by eta Vf by eta Vt minus Is. So the Is is reverse saturation current, which constitutes for a which is very small compared to the rest. So this can be approximated as, this is often approximated as Is into e to the power of Vf by eta Vt. This is what we generally consider. Now with that, if I write the collector current, I can write collector current as Is into VBE, because that is a forward voltage across the junction, emitter base junction. VBE divided by, I can write it as eta Vt, or I can simply write it as Vt. Right. So this is the collector current. All right. Now, so let me just look at let me just look at this circuit. You can see, or let me, yeah. So if you look at the circuit, we can see that the emitter current here is basically the sum of these two. This is base current and this is collector current. So that is one more relation what I'll take it here. Emitter current is written as the sum of base current and collector current. That is another very important relation. Now we should know how these are related. So IC and IE, how these are related. I hope this also you may be able to recall. IC and IE are related using a factor called alpha. We call this alpha as current gain factor. Then again, IC and IB are also related by some other factor called beta. Beta is also current gain. Right. With this, if I go for this IE expression can be further written as IB plus IC is anyway beta IB. So I can write this as beta plus 1 into IB. So IE can also be written as beta plus 1 into IB. These are various relations what we use. Now I know that the emitter current and collector current are related as emitter current is written as IC by alpha. So if I want to get the expression for emitter current, I can write it as IS by alpha into e to the power of VBE by VT. So the difference here is your emitter current will be slightly larger than collector current because there is some current or some yeah, that is given from this expression, right? Because emitter current and collector current almost you can consider almost equal, but the difference is actually the base current. That is what you will see in both the expressions. So this expression and this expression, the difference is only the alpha in the denominator, and alpha value is the very small. It is lesser than 1. Yes, Parnika. Parnika, your question is why it is not VCB, why it is VB. Yes, very good. So you look at this diode. How I have written the diode current equation. Diode equation here is depending on the reverse saturation current and the forward voltage, or the voltage which is making the junction forward bias, not reverse bias. Isn't it? Is it clear, Parnika?
Sir, one doubt.
Yes. One
You
second,
said that.
Karthik, 1 second. Let me just get a response from Parnika. Parnika, is it clear? I have taken a diode and I have written the diode equation. And in the diode equation, I have marked VF, where VF is actually the voltage which is making the junction forward biased. So similar way, the electrons are flowing from here. That is electrons reaching collector. Right. Now that current is because of the forward bias voltage between the emitter and base, which is basically VBE. Parnika, please come back or please put a message. If it is not clear, I'll explain. Yes, Karthik, go ahead.
Sir, for that you said the forward voltage, which makes it, I mean, the voltage which makes it forward biased, right?
Yes, yes.
But VB is for the other junction, not for this junction.
Yeah, right. So so we know that this PN junction, the collector base junction, is not forward biased at all. Right. And the electrons is the one who is emitting the electrons. Well, collector, why the collector is able to collect is because the reverse bias junction here, since it is reverse biased, and because of this larger voltage, and because of the very thin nature of the base, these electrons are reaching collector.
Okay, sir. Okay.
Isn't it? Is that clear, Karthik?
Yeah. Okay.
Okay. Yeah. Okay, Parnika. Thank you for the response. So this is how we relate the expression. So we will see that the emitter current is slightly greater than collector current, but in some cases we will see how when all at which all cases will approximate both emitter and collector as same. So this you will understand whenever you find the values numerically as IC and IE, the difference will be very small. And just to bring in the relations of alpha beta, I hope these things you will definitely recall. Alpha by 1 minus alpha is called as beta. and alpha can be written as beta by beta plus 1, again from the same expression. Right. So I'll just give a simple exercise. Just calculate what is alpha value for beta equals 50 and alpha value for beta equals 150. You will see the difference in the value of alpha. Can you guys calculate and just put the numbers there? Oh, Parnika, okay, you have that question again. You asked again, or? Oh, that was the previous question itself. Okay, sorry. Yeah. All right. Alpha for beta 50 is 0.98 and alpha for beta 150 is 0.99. Right. Yes. Yeah. So this we will refer it again. Even the beta is changing in large numbers, the change in alpha is very, very small. Yes. Thank you, Bhavana, Manikandan, Abhirami, Sai Kiran, Kirtana. All right. So I'll just show you the structures, how we have drawn MOSFET in a similar way. If you draw BJT, it will be something like this. You will have N region from which you will have an emitter. You have a very thin base. And we'll have a, so this is P, this is N, and this is the collector port part. Right. So from the structure itself, we will understand that this is not a symmetrical device like a MOSFET. Not a symmetrical device. And that means we cannot interchange E and C. Emitter and collector cannot be interchanged. Now, if you do that, the biasing will be actually, it will go to reverse active, which will not be a useful circuit at all. Right. But in the case of MOSFET, it was not like that. MOSFET is a symmetrical device, and you can interchange the terminals. You can interchange the terminals in the sense wherever you are connecting higher voltage, that becomes drain for a N MOSFET. Wherever you connect lower voltage, that becomes a source for a N MOSFET, and the other way for a P MOSFET. Right. I hope that is clear. And now let me just draw the symbol of BJT. I can take questions if you have after some time. So this is the symbol where this is base, collector, and emitter. And we should know the current direction. Emitter current is in this direction. This is base current, and this is collector current. This is for NPN transistor, and similar for a PNP transistor. This is collector, base, and emitter, where this is emitter current, this is base current, and this is collector current. So here you can see that in an NPN transistor, emitter current is flowing outside, so other two currents are actually coming in. But in PNP, emitter current is flowing in, so the other two currents are flowing out. So at this point, you can have one more difference with respect to MOSFET, because MOSFET, there was no gate current. So if you compare the terminals, it is like a base is, so in place of gate, now you have base, right? Now, if you look at base, you have a base current, you have a finite base current. But in the case of MOSFET, you had a zero gate current. So that makes difference. So one difference is the input impedance of a MOSFET, say because of zero gate current, was infinity, but in the case of BJT, you have a finite input impedance. That is one more difference. Let me just write that here. In BJT, base current is non-zero Therefore, finite input impedance and in MOSFET input impedance. So in every places we'll make these kind of differences with respect to MOSFET. In MOSFET input impedance is infinity because we have gate current equal to 0, right? So with that, I'll just take you to the 3 different configurations which is possible. We have 3 configurations: common base, so common base means base is kept common both for input and output. So we will give input here and output will be taken from collector. We call this as common base configuration. Now if input is given to base and output is taken from collector, then we call this as common emitter configuration because emitter is common for both input and output. So this is CE config, and if you are giving input to base and output from emitter and you have collector in common, we call this as common collector config, right? So these are the 3 different configurations what we can use with BJT. Right. So what we discussed today, we started with the structure of BJT. We have looked at the operation of BJT in active region, and with that we have written the current equation by comparing with the diode. We have written all the current equations relations, and then we looked at the structure and understood that MOSFET is not a symmetrical device. Sorry, BJT is not a symmetrical device, and we cannot interchange the terminals and the symbol. And then we saw the 3 different configurations, right? So now we will specifically look at two numericals just to have an understanding with the current equations. Let me give this question to you now. Probably I'll just connect a voltage here. We call this as V1, this as V2, and the voltage which is connected here is V3, which is giving IC1, and this is IC2, and this may be some current. Maybe you can call it as I3 or something, current which is flowing from here. So this is transistor Q1 and this is transistor Q2. So assume that both are identical. This Q1 and Q2 are identical. That can be assumed. So these two are identical is one condition, and assume both are in active region also. Both operates in active region. Now the question is determine what is this difference V1 minus V2 if IC1 is equal to 10 times IC2. So you are asked to determine V1 minus V2 if IC1 is equal to 10 times IC2. It's a simple exercise so that we will be familiar with the current equation of BJT. So can you guys try? I no need to put the answer there. I'll check and then you can give answers. So Irshad is there, Irshad? Irshad, are you there? So Manjunath Prakash, are you there? Manjunath Prakash.
Yes, sir.
Okay, Manjunath
Hello.
S. Yeah, you're right. Yeah, Manjunath S.
Yes, I'm.
Manjunath GS. Only Manjunath Prakash is there. Okay. Palak is there. Palak. Palak. All right, not there. Okay. Yeah, so now you can post answers in the chat box. So maybe one more thing you can assume, all these are considered under temperature, this 300 Kelvin. I don't know how many of you know what is this VT as volt equivalent of temperature. If you're not aware, I'll explain now. Okay, it is lantern. Okay, VT is also there, right? Yeah, the answers are close. Okay, let me explain that here. Now I know the current equation. I know what is the current equation for a IC of a BJT is known. IC can be written as IS into e to the power of VBE by VT. Approximated equation is this, right? Now, if I write for IC1, IC1 can be written as IS into e to the power of VBE is V1 by VT. And similarly, when I write IC2, it is IS into e to the power of V2 by VT. And we are asked to find the difference of V1 and V2. So to find the difference of V1 and V2, what I'll do is I'll take the ratio of these two. So IC1 by IC2 I will take. So IC1 by IC2 can be written as IS will get cancelled. So it is e to the power of V1 by VT divided by e to the power of V2 by VT. So IC1 by IC2 is given as IC1 by IC2 is 10, that is given. 10 is equal to e to the power of x by e to the power of x1 by e to the power of x2. You can write it as V1 minus V2 by VT, or when you solve this, we can write V1 minus V2 as VT into ln of 10. So what is VT? VT is in fact KT by Q. You can take T temperature as 300, and this value is approximately 26 millivolt VT. Now when you substitute that here, 26 millivolt into this lantern is somewhere close to 59.9 millivolt or something. Yeah, 59.87 millivolt. Yes. Yeah, if it is V2 minus V1, I hope, yeah, then there will be a minus, but now it is V1 minus V2, so it will be a positive voltage. I hope this is clear. If you have doubts, please please ask. I'll clarify. Meanwhile, I'll give one more question, just to get you familiarized with this current equation. This is 3 volt. This is 1 kilo ohm resistor. Here you are connecting DC voltage. Say it is somewhere close to 750 millivolt. And this is the point where you find V out. Right. So anyway, V out, what we are looking now is a DC voltage. So given that Is is equal to 5 into 10 to the power of minus 16 ampere. The question is to find V out. We are asked to find V out. Can you guys try?
So could you repeat the question?
Yeah, the question is to find V out. You're asked to find V out. The given data is Is given as 5 into 10 to the power of minus 16.
Okay, sir.
Yeah. So if you're getting answers, you can post it. Tanush, are you there? Tanush.
Sir, one doubt. What about temperature, sir?
Oh, temperature same.
Okay, sir.
Yeah. Tanush, are you there? Yeah. So please try out and let me know what answer you're getting. Renuka, are you there? Renuka.
Yes, sir.
Okay. Mihir Ji is there? Mihir Ji. Online. So what is the answer? What answers you are getting? Yeah, Harshita got 1.4. Abhinami 1.3. Yes, 1.3. Yeah, answers are close. Yeah, close to 1.3. Joel, did you get the answer? Joel. Hello, Joel. Oh, Joel is not there. Okay. Okay, so how to solve this? So what you are seeing is a transistor which is biased using two voltages, one on the base and one on the collector side. So the first thing is I know Is. With Is we can directly find what is IC. So let me mark the currents here. So this will be IE, this is IB, and this will be the IC current. So IC I can directly write as Is into e to the power of VBE by VT. If you want, we can take -1 also. So VT is 26 millivolt. Now we will get IC. What is IC value? I think it is close to 1.7. Check the answers. It is close to 1.7, I guess. So that is IC. Now this IC current is actually flowing through this resistance of 1K. So you are asked to find what is V out. V out is actually the voltage at collector with respect to emitter, right? So now what you can concentrate is actually this part where you can write 3 voltage. This is plus minus. Now current is flowing in this direction, so there will be a drop across 1K resistance. So 3 minus 1K into the current IC minus V out is equal to 0, or you can write V out as 3 minus 1K into this 1.7 milliamps. That will give you answer very close to 1.29 or something, 1.3 I guess, 1.3 volts. Right. So this is how you should solve these kind of questions. So this is a very simple question. I just given, yeah, for you to get practice. 1.6. I don't think 1.6 is there. Bhavana, can you check again? It will be close to 1.3. All right. So with this, I'll be winding up today's class, and we'll be continuing from Monday with the different configurations and the characteristics. So thank you for joining.